Okay, so what I thought I'd do today is I did sort of review of chapters 16 through 18 last time, so I thought I'd go through the rest of the chapters relatively quickly, and then answer whatever questions you want to ask me. Okay, any questions about the final logistics, anything else? Okay, so so chapter 19. I'm not going to say a whole lot about. I think I'll sort of write down all the words that I think you should know from chapter 19. If I were to ask a question about chapter 19, I would like you to use correctly the words that I am going to put on the board, like whatever words are appropriate. Like if it is a one of the kinds of samples that I've mentioned and that I'm going to write down, I'd like you to say that. If it has a particular kind of bias, I'd like you to know the words in addition to being able to describe it. So for full points, so you sort of get partial credit for any question that has to do with chapter 19 if you say some things about, some correct things about it. But to give full points, I'd like you to actually use the words, this jargon from the class. So the context of this chapter 19 stuff is that we have some statistic which is somewhere around the parameter, but it could be off because of chance error or bias. And this chapter deals mostly with the bias. All the other chapters deal with the chance error pretty much. And I'll just write down, what these things are and what the kind of big picture things are. Population is the group. I'm going to be a little bit more brief here than I was when I first went over this stuff, but just sort of to remind you. This is the group sampled from. You might think of these as the people in the box or whatever's in the box. The sample is a subgroup of the population. And you might think of these as the draws. Okay. And when I say sample, I don't necessarily mean a random sample. We talked about a lot of different kinds of samples, but it's some group that's a subgroup of the population, and we know some information about them. So what we want, usually, in the context of this, is the parameter. That's what we're trying to estimate. So the parameter is, I'll just say, just briefly, something about the box. It's like the percentage of ones in the box, or the average of the box, something like that. And in the context of this chapter, at least, it's unknown. So typically unknown. So the statistic is typically what we know, and we're using that to estimate the parameter. So it's I guess, to be sort of consistent, this is something about the sample, like the percentage of ones in the sample, the average of the sample, whatever. Okay, so that's some sample value, and this is typically known. So the context or the idea of what's going on here is that we're going to use the statistic to estimate the parameter, and the statistic should be, the logic of it is that the statistic should be pretty close to the parameter. It might be off because of chance error, it might be off because of bias. And the chance error part we study pretty thoroughly. The standard error measures the likely size of the chance error. The bias part, what the Gallup poll says on their website and what typically is done in practice is that you do everything you can to minimize bias, and then you, to some extent, ignore it. So what they say is that these things may be a problem, but really when they give you the results, when they say like the margin of error is plus or minus however many %, they're not talking about the bias part. It's sort of buried in their explanation of technically what they did for their survey or for their sample. I'm not saying that's right. I'm just sort of saying that's what's typically done, is to do what you can and then for the most part, ignore the bias. So, okay, so bias is some kind of systematic error as contrasted with chance error, which is random. Okay, so bias is systematic error. And I talked about 3 kinds. Selection. And I think I mentioned this at the time. I sort of think of these in the order that they happen. Selection bias occurs as you're picking the people. And it has to do with any systematic differences between, I'm not going to write all this down, but it has to do with systematic differences between the people that are selected and the people that are not selected. So if you have a simple random sample, there shouldn't be any systematic differences between the people selected and not selected. It's just the only difference would be because of the randomness in the sampling process. If, however, you have some other kind of selection process, you may have results that will be biased for a variety of reasons. And there are examples in the book of this. I guess one that's coming to mind from your homework is that if you do door-to-door interviews and interview only, you only get to talk to people where there's someone home. Well, the houses where no one's home may be different in some systematic way than the houses where there is someone home. And in that homework problem, you would expect that the houses where no one is home probably are on average smaller than the houses where there is someone at home. So that's all part of selection bias, that you want to kind of worry a little bit about how the people that are selected are going to be different than those that are not selected. So the second kind is non-response. So that has to do with, I'm sorry, you know what? I was getting ahead of myself. I just described non-response bias. Non-response bias has to do with whether or not people are home. The selection part is the houses you actually go to, right? So if you go to a house, that house is selected. If there's no one home, that's considered to be part of non-response. That it's sort of not the fault of the interviewer. They selected the house. Okay. Now, it's not kind of. You might think of non-response generally as being like they slam the door or refuse to talk to the interviewer or something like that. But it really has to do with anything that's not part of selection. So if your house is selection and then they don't get a response from you, that's thought of as non-response bias. Okay, so then the last one is response bias. So response bias has to do with either question wording or like the order of candidates or the order of responses that are read to the person that's being interviewed. So I think I described some examples of this. Another one that I didn't really, I think, emphasize is if a question is particularly sensitive, you might get different results if you did it totally anonymously as opposed to in some public way. So if I asked some very sensitive question to the class and just asked for like a show of hands or something, I might get different results than if I did some completely anonymous, I don't know, phone poll or something. Okay? So that's also part of response bias. It sort of has to do with how the question is asked. Okay, questions about any of these? Okay, so again, if there is a question, question on chapter 19, I might ask you to describe what's going on using some of these terms, and I might ask, talk about some of these biases, maybe which one of these do you think is the most important, or maybe comment on one in particular. And so you should know these terms. The kinds of samples. So there are probability methods which somehow involve chance. So something is done randomly in the sampling process. So the ones that I care about are a simple random sample, so remember the simple random sample is done without replacement. And random digit dialing is not, it's sort of about as good as you can do in the real world. You can't really get a true simple random sample for any kind of large population because we just don't have lists like that. Like you don't have a list of all the adults that live in California or something. So it's difficult to take a simple random sample of them. But we can at least do something random with phone numbers. So that's another kind of probability method. And the cluster sample, possibly multi-stage, is another one. So a cluster sample involves well, the idea of a cluster is to get one group. So maybe it's a regional group or some kind of geographical way people are divided up geographically, possibly like by rural or urban or by just by counties or whatever. So it's multi-stage if that's done in different stages, like choosing a random state, then choosing a random county, then choosing a random bunch of households or something like that. One fairly common example of a cluster sample that isn't multi-stage would be to take a simple and random sample of households and interview all the adults in all the households. Okay, so they're clusters in the sense that you're taking all the adults in a household. So that's a cluster of people that have something in common. But there's just, like I said, one stage. Okay, questions about any of those probability methods? Yeah. Well, so literally what the Gallup poll does when they do random digit dialing involves a little bit of both. So you might think of what the Gallup poll does as being kind of a special case of a cluster sample, because what they do is they do take these random areas as part of their sampling process, but they do it. Actually, I shouldn't say that. I guess they don't take random areas in the same way. They construct their sample to get a simple random sample of phone numbers in each of different areas. But those areas are not selected randomly. I think they actually get some from every area, right? So they aren't randomly choosing states. They're actually making sure they get someone from every state. If states are one of the ways I don't think states is actually one of the ways they divide it up, but they're not doing random states in any case. So there sort of aren't any clusters for random digit dialing. You're not picking these random areas in the same way that a cluster sample would be done. A cluster sample is also more general in the sense that it doesn't have to be a phone sample. It could be door to door and anything else. Does that clarify a little bit?
So random digit dialing is only for
Yeah, it's actually dialing numbers on a phone. Yeah. Okay. Any other questions? Yeah.
So in some cluster samples, even though they are a probability method, there's sometimes there will be selection bias, right?
Yeah, he's asked if there can be selection bias in a cluster sample. Yeah, there can be. And also, so simple random sample is the only one where you won't have selection bias. Random digit dialing, you'll have selection bias because not everyone has a phone, and some people have maybe multiple phones or share a phone or whatever. And in a cluster sample, depending on how the clusters are taken, you may or may not have selection bias. So the question is whether or not, essentially whether or not some people are more likely to get into your sample than others. So for example, if I took like 5 random states, Californians would be less likely to show up than people from Wyoming, right? Because if we take 5 states, sure, California is just as likely to show up as Wyoming, but if California is in the sample, you still have a really, really small chance of getting in the sample itself, whereas if Wyoming is chosen as one of the states, you have a higher chance since Wyoming doesn't have as many people. So in that sense, if you choose a cluster sample in a way where the clusters are of unequal sizes, then some people are going to be more likely than others to get into the sample. Okay? Yeah? Any other questions about that? Okay, so non-probability methods. So these don't involve chance. The book talks a fair amount about quota samples. So in a quota sample, the people are sort of hand-picked by an interviewer, and that process, since you're not doing it explicitly randomly, can introduce bias. If some people are more likely to be chosen by the interviewer than others, then that can introduce bias into the sampling process. The thing that's sort of nice about a quota sample is that, at least with respect to the variables that you're set quotas on, you sort of get it right. You know, like if your quota is based on making sure that you get the same percentage of women in your sample as there are in the population, then at least with respect to that variable, you'll kind of get it right. Whereas a simple random sample may not. Right? A simple random sample, you may get too many or too few women at random. So in that sense, quota sample might be good for some things. Like if there's a variable that's really, really important, and you really want to make sure you get it right, you get the sample right for that variable or for a couple of variables, it might be good to do that rather than leave it up to chance with a random sample. The problem is, and the thing that statisticians don't like about non-probability methods, is that you don't have any way of knowing what the bias is like. Okay? Chance error we've studied really well, right? So we know, based on calculating the standard error and things like that, we know randomly about how far things are likely to be. So we, at least, even if it's not perfectly accurate, even if the statistic is not exactly the same as the parameter, we have a good idea of how far it's likely to be off because of chance error. The bias part is harder, okay? So that's why a lot, statisticians will generally prefer to do something random rather than doing something that's biased. So, okay, so that's that. So quota samples, sample of convenience. I sort of gave the example of this class as a sample from Berkeley students or something like that. It's not done in any random way. It's just because it's a convenient group of people to ask. And again, that's likely to be biased. And the last one, I sort of generally said media polls, and especially internet polls are very common. So again, there's nothing random going on. You just get whoever happens to respond. So that's often biased for a variety of reasons also. Okay, questions about any of these? Yeah?
So is an SRS the only one that works for like finding
Right, good. Yeah, so a simple random sample is the only one officially that the box model works for, that you can do all the calculations for. Sometimes there are examples where there's random digit dialing, and the question will say something like, you can assume this is like a simple random sample. Okay? Officially, simple random sample is the only case where it actually is true, like the standard error is the right thing. Yeah, but like I say, there may be questions where the data is gathered in some other way, because that's typically what happens, right? We typically don't have quite exactly a simple random sample, and this is one of at least one of the better things to do. Yeah, so we'll sort of analyze this and kind of recognize that, yeah, it might be a little bit biased, but It's pretty close. Okay? Any other questions, thoughts? Okay, so that's chapter 19. So chapter 20. Well, actually, there's not that much to say about chapter 20. I'll just maybe squeeze it in here. So chapter 20 is the first time that we deal with anything other than sums of draws. So we deal with percents in chapter 20. So we have expected value for percent is the percentage of ones in box. Okay, so the stuff in chapter 20, expected value and standard error at least, only makes sense for a box with zeros and ones in it, because we're just talking about percentages of zeros and ones. But keep in mind that other boxes can often be converted to a 0-1 box. Like if I wanted to think about the percentage, like if I roll a die over and over again, the box would be 1, 2, 3, 4, 5, 6 if I were actually adding up the die rolls. But if I'm interested in the percentage of sixes or something like that, I could convert that into a 0-1 box. Okay, so SE percent is SE sum divided by the number of draws times 100%. And there's not a whole lot to say about chapter 20. It's basically those two equations and then the correction factor. So the correction factor the formula is square root of population size minus sample size divided by the population size minus 1. And I guess I'll say it this way. It's the way you use it is that you take a standard, if you want the standard error without replacement, you take the SE calculated with replacement, which is the standard SE that we're used to calculating, and multiply it by the correction factor. Okay, so this is okay to use for any simple random sample, which is without replacement. And so it's sort of technically correct to use. I don't care particularly if you use it if the population size is very huge. So if the population is California and I'm sampling 1,000 people out of California, this is going to be basically 1 anyway. So multiplying by something that's basically 1 is not going to change your answer. So my rule about it is that you must use when, I guess I'll say it this way. You must use for a simple random sample. For simple random sample when sample size is at least 10% of the population size. Okay? Questions about that? Okay, so that's chapter 20. Chapter 21 is when we first encounter confidence intervals. So I'll say confidence intervals give a likely range for a parameter. So that's just intuitively the idea of making a confidence interval. Is that we want to get not only an estimate of what it actually is, but how far that estimate might be off, how much that estimate might be off, or to say it this way, to get a range where we're pretty sure that the parameter is in that range. Okay, so we're still going in this general world where the statistic is somewhere around the parameter but might be off because of chance, error, or bias. But for making a confidence interval, you want to make sure that there isn't bias. The confidence interval sort of doesn't make sense if there's bias, whether it's selection bias, non-response, or response bias. So having said that, I might ask you on the test to just do it, like make the confidence interval, and then I might ask as a later part of the question, sort of comment on it or state any possible kinds of bias or whichever one you think is the worst, something like that. Okay, so yeah, so like I say, making a confidence interval in general, if you have bias, is not really honest. Like I'm not really 95% confident that it's in there, the parameter's in there, if there's bias that might, make it way off. The confidence interval just deals with the chance error part. So, okay, so that's that, and 95% confidence interval is statistic plus or minus 2 SEs, and like 68% will be plus or minus 1 SE. I could ask you for any kind of confidence interval I want. You just have to make sure they match, right? Whatever I ask for, look it up on the normal table and figure out how many SEs it would be. So 95% is 2, 68% is 1. If I ask you something else, look it up. So yeah, that's the very basic idea. Any questions about that? Okay, so I'll talk about some of the more subtle issues that I talked about before. First is to get at this bias issue that you need a simple random sample or draws without replacement. And that will guarantee that you have no selection bias, at least. Oh, sorry, I'm sorry, draws with replacement. Simple random sample is without replacement, or it could be draws with replacement, and that will guarantee you have no selection bias. And also, confidence interval only makes sense when no bias of any kind. Okay. So I think you should at least think about it. Like if, I don't know, examples like confidence interval for height or test scores or something like that, you probably don't have non-response or response bias because you, well, in particular, if I don't tell you something about that piece, say 80% of the people responded or something like that. If I don't tell you, you can sort of figure that everyone in the sample responded, everyone gave their height, everyone gave their SAT score, whatever. So there isn't a problem with non-response bias. And for something like that, presumably people don't lie or something, right? Their responses are honest, so there shouldn't be any response bias. So for a lot of things, you could sort of just, by common sense, see that there probably isn't any bias, and that, except for like selection bias, has to do with the sampling procedure. So this first part you can kind of check directly, and the rest you might need to think about a little bit, whether or not you think things might be biased. Okay, questions on that part? Yeah. Yeah, there's no sort of magic response rate where if you have like above 80% response rate, everything's good, and if you have below 80% response rate, it's no good. It's a continuum. The better the response rate, the less you should expect there to be non-response bias. Having said that, it also depends somewhat on what you're asking. Like, I think you need to think a little bit about how are the people that got into this, how are the people that responded likely to be different than the people that didn't respond? If it seems like they're probably about the same, that there's no real systematic difference between the people that respond and those who don't, then it's less of an important issue. Okay? I'm not saying it's no issue at all, but let's see. Let's say well, so something that I always feel like is since we just did evaluations last Thursday, the people that come to class probably enjoy lecture more than the people that don't. So I always feel like things are a little bit biased, right, in that regard. And I do sort of try to, some extent, have, like I wouldn't want to have evaluations today because attendance isn't so great, right? I try to do it on a day where I think at least it's reasonable to think that people will be coming to class more. I don't know. And I guess it's an issue even more for GSIs that I guess you have homework due every week, so probably you have sort of a reason to come. But for example, I might try to, if I were a GSI, I might try to do evaluations on a day that quizzes also due. People might be more likely to come if both those things are due rather than just one, or certainly if there were a day where nothing was due, you might expect that attendance would be a little bit lower. Okay? So I guess I'm raising that as an example because I feel like that is something where even if, like, I don't know, maybe typical day, maybe 2/3 or so people come to class, maybe 3/4, I don't know, something like that. That's fairly high percentage of the class. I think the Gallup poll would be quite excited if they got that kind of a response rate. But since the thing that I'm interested in is probably pretty related to people's attendance, that might be more of a problem. Whereas if the Gallup poll is doing something like I don't know, asking a question where it's the people that respond are fairly similar to the people that don't respond, that it probably makes less of a difference. Yeah. I mean, really, the Gallup poll probably has at least a little bit of a problem with almost any question they ask, because we know that older, more conservative, richer people tend to be more likely to respond to them. Okay, so other questions, thoughts? Okay, so for exam purposes, first of all, if I don't tell you the non-response rate, or the response rate, you don't have to worry about it. I mean, unless I explicitly ask you, like, well, do you think this is an issue, like the Gallup poll or something like that. If I explicitly ask you about it, you might wonder. But then, even if I do give it to you, you might think a little bit about whether or not you think the people that respond are likely to be different, and kind of address that. Okay. So, let's see. So that's that issue. And then, oh yeah, so the probability histogram for the statistic, and the statistic is going to be either a sample percent or average. Must look like the normal curve. So the checks that keep coming up, came up in chapter 18, come up here. The first one is at least 25 draws. And the second one is that you want to have plus or minus 2 SEs be in the range of possible values. So in the chapter 18 context, I go expected value minus plus or minus 2 SEs. In this context, I can't do that because I don't know what the expected value is. I know the statistic, but I don't know the parameter. The parameter would be the expected value for the statistic. But since this is all I know, this is my check. Should be okay. Should be, I guess I'll write it out, in range of possible values. So if I'm dealing with percents, that range should be between 0 and 100%. If I'm dealing with averages, it needs to be, this range needs to be between the smallest possible thing and the biggest possible thing. Okay? Questions on that part? Okay, so then, oh yeah, so I guess I wanted to mention, you should make this check even if you're doing a 68% confidence interval. Okay? This check is to make sure the normal curve works at all. So if the normal curve doesn't work at all, then you shouldn't expect to have 68% of the area within one standard error. So that 68% confidence interval would be invalid based on this check. Okay. So the third thing is this idea that confidence intervals are for parameters. And chance is for the sample value or the statistic. The sample value, the draws somehow. There's randomness involved in the sampling process. There's not randomness involved in the parameter itself. So that's why we have this like different language of confidence for parameters. And we don't talk about chance with parameters, and you wouldn't make a confidence interval for a sample value. Okay, I think that's it for now. Yeah. Okay, any questions on that one? Okay, so that's chapter 21. We skipped 22. Chapter 23, as I mentioned at the time, chapter 23 kind of goes back and does a lot of stuff from chapters 18, 20, and 21, but in terms of averages instead of percents or sums of draws. So really the only thing in chapter 23, let's squeeze it in the bottom here. I guess I'll put it on a new board. The only thing that's really new is the formulas for expected value and standard error. So expected value for the average of the draws is equal to the average of the box. And the standard error for the average of the draws is equal to the SE sum divided by the number of draws. Okay, so that's really all that's really, I don't know, new in chapter 23. Chapter 23 is pretty long because it goes through a lot of these same examples and issues for averages, but there's not really anything that new in it. These same ideas or issues are still relevant for averages. Yeah. Okay, any questions about chapter 23 stuff? Okay. There are a couple little differences in thinking about averages as opposed to percents, because if you're dealing with percents, you have a box with zeros and ones in it. If you're dealing with averages, the tickets are maybe a little bit more abstract. They may be incomes or SAT scores or something like that, and you don't know really what the composition of the box is so much. Whereas in chapter 20 and 21, even if you're estimating the parameter, you at least know all the tickets in the box are zeros and ones. Okay, so it's a little bit more concrete information about the box as opposed to averages, where you sort of really don't have any idea what the numbers themselves are. Okay. So, right, so we skipped 24 and 25, and then chapter 26 gets into hypothesis tests. I guess I get that. Well, so for the final, I would like you to have all these steps in any hypothesis test you do. So I'll give these instructions on the exam also. I'll just say basically, if I ask you to do a hypothesis test, include null hypothesis, alternative hypothesis, test statistic, p-value, and a conclusion, okay? And so that's what I'll tell you. And then in the null hypothesis, you should have two parts. You should have a chance statement, something like the results can be explained by chance, or something like that. That's 1A, chance statement. 1B is something particular to the problem. So you don't have to say this explicitly in terms of a box model, but I think that's often the easiest way for you to say it, is to say, what does the null hypothesis say about the box or the population? Does it tell you the average of the population? Does it tell you the percentage of ones in the population? Whatever. It says something about the box or the population. So yeah, so it doesn't have to be exactly like that, but I think that's often easiest. For something like the card guessing example, the very first one I did, the null, this part of the null said that I was guessing at random. So guessing at random gives you enough information to make the box. 4 zeros and a 1. 1 correct guess, 4 incorrect guesses. So somehow that part of the null should tell you something about the box. Okay, questions about the null? Okay, so then the alternative. Okay, so part A, again, is some kind of a chance statement. And this is it really is the alternative to the null, meaning that the data or the results can't be explained by chance, or something similar to that. And then again, something particular to the problem. And so when we did chapter 26 and 27, we hadn't talked about one-sided versus two-sided tests. Now, after doing chapter 29, there's something that I would like you to include here, which is that this should determine whether or not you're doing a one-sided or two-sided test. So it should, I guess, imply whether one-sided or two-sided. Okay. So basically, it should either specify a direction or not. If I say something like, I can do better than guessing at random, better than guessing at random implies I need to do better. I need to go, get in one direction. If I'm trying to claim that Botox helps people recover from strokes, well, I wouldn't conclude that it helps them if it makes them worse. So since I would only reject the null on one side, I should be doing a one-sided test. And again, that should be stated here, at least implicitly. If I'm testing to see whether or not a die is fair, the example I did last week, well, getting a result that's too high would make me conclude that the die is not fair. Getting a result that is too low would also make me conclude that the die is not fair. So since I would reject the null on either side, I should do things two-sided, and this should reflect that. So for that example, this would just say the die is not fair. It doesn't specify a particular direction. Okay? And that should come from the problem. The problem should give you enough information to decide whether or not a one-sided or two-sided test is appropriate. Basically, what it comes down to is you should think about, well, if the data were on the other side, would I reject the null? And if you would reject the null based on data that's in the other direction, then you should be doing it two-sided. If you only would reject the null on one side, then one-sided. Okay, questions on that? Okay, so then third step is a test statistic, which could be either Z or T. And I'll talk a little bit about the t-test after I go through this. But basically, in either case, the test statistic is going to be observed minus expected divided by standard error. And all of this is based on null. So you assume the null hypothesis is true for this calculation. And in particular, the expected value is always going to come from the null somehow. The standard error might come from the null, or it might be based on the bootstrap method. It might be based on the sample. OK, questions about that part? OK, so then next step is the p-value. And I'll just define it. The p-value is chance of data like we got or more extreme given that null is true. Okay, so that's that. And then, finally, conclusion. This is step 5. So I don't care if you explicitly do it kind of outline form that I do, but all the bits should be in there somewhere, okay? And I guess it's a little bit easier to grade if you do it in outline form like this. So I guess I'll mildly encourage you to, but you don't have to. You also don't have to do a box model if you don't want to. I think a box model is a way to get partial credit if you otherwise do things wrong, but I won't make you. Yeah?
Did you write out the definition of the p-value?
You don't have to write out the definition of the p-value, right? Just calculate the p-value. Yeah, so it's basically, p-value is this. You have like a z or a t, and that's your p. Okay. Possibly two-sided. It might include the other side too. Okay, so conclusion should also have 3 bits. The first is a bit of statistical jargon, which is basically, do you reject the null hypothesis or not? So you reject it at some level, or you can't reject it. One of those conclusions. So I'll just say reject null. And then a chance statement. So if we're rejecting the null, that means we don't think that chance is a good explanation. If we can't reject the null, that means that we think that chance could be a reasonable explanation. So something along those lines should be your B part. And then the C part is something particular to the problem again. So if your conclusion for the actual problem is that you think I can do better than guessing at random, or I can't, or whatever, something particular to the problem. Okay, questions on any of that hypothesis? Yeah. Yeah. Yeah, she said if you want to say something particular to the problem and refer to the box, is it okay to talk about the box without actually drawing it? As long as it's clear what you're doing, yeah, that's fine. Yeah, you don't have to have it drawn out explicitly. That's fine. Okay, any other questions? Yeah. How do you do what? I'm sorry? Yeah, it's twice as big. Yeah. So yeah, you can think of it just as doubling what you would ordinarily get, or in practice what you really would do is you would just sort of take 100 minus this. Right? 100 minus the area in the middle would be both sides. Okay. Any other questions? Yeah. To do a hypothesis test, does the data have to follow the normal curve? No. What has to follow the normal curve is basically the same thing as you have here. the probability histogram for the sample percent or the sample average must follow the normal curve. So you have to make these checks. Okay? Yeah, so it's not important that the data itself or the whatever you're looking, like the box or something, follows the normal curve. Okay? Yeah. Yeah, so she's asking basically, oh, I guess, right, so you're talking about the last part of chapter 27 where you do a treatment control, that part? Yeah, so if you have a treatment and control situation, you have to word things a little bit differently. So like for the example I did with Cal faculty and Stanford faculty, the null hypothesis says that both universities have the faculty of both universities have the same percentage Democrat. So we are kind of implicitly making these statements about these two boxes, the two populations of faculty. For a treatment control situation, you have to be a little bit careful about how you state it. I have never found a way that I like to state the null for that situation, for the treatment control situation, without somehow talking about a box. Because you only have one population, so you can't say the percentage of ones in that population is the same as the percentage of ones in that population. It just doesn't make any sense, right? Of course it is. The only way to have it really, have the null really make sense there, I think, is to say something about like this left side of the ticket, right side of the ticket kind of thing, okay? Now you can word that a little bit hypothetically in sort of a way like your chance of getting better with Botox is the same as your chance of getting better with the placebo. That's sort of implicitly saying something about the left and the right side, because the left-hand side represents ones and zeros where you get better if you get Botox. The right-hand side is ones and zeros depending on whether or not you get better if you get the placebo. So if you say something like that, your chance of getting better is the same. Yeah, I mean, even that is not quite right. Really, it should be kind of the percentage of everyone who would get better with the treatment is the same as the percentage of everyone who would get better with the placebo. Because really, it should be a little bit of a global statement and not just about you, right? Like your chances of getting better. Okay, yeah. Right, that's a good point. It's just the people that are in the population, in the box itself. Okay, so if you like that Botox experiment, the second one I think had 126 stroke victims in the box, and strictly speaking, our conclusion is only valid for those people, right? It doesn't say anything about whether or not, I sort of mentioned a slightly silly example of like if my hand hurt, I would not be injecting myself with Botox, right? I'm not part of the population, and I'm not really similar to that population. So if you it's strictly speaking, it's just saying something about that particular box. If you have stroke victims that are similar, at least it makes sense probably to think that people that are like the people in the box will respond in a similar way to Botox treatment. Okay, but that's a little bit subjective. Like how similar do the people need to be for them to look the same as the people in that box? Does that make sense? Okay, but like I said, strictly speaking, your results are true for that box, for that population. Okay, any other questions, thoughts? Yeah. She said, so when would you want to use a one sample test versus a two sample test? Well, the sort of, I don't know, smart ass reply. Can I say ass? If I'm being videotaped, I don't know. The smart ass reply is, well, if you have one sample, do a one sample test. If you have two samples, do a two sample test. Which is right? If you have two random groups of people, then you need to do a two sample test. If you have one random group of people that you're comparing to some fixed number, then you would do a one sample test. Does that make sense?
What if it's the same group of people but compare at different times?
Same group of people compared at different times. Well, is it the same people? Like actually the same people, or is it a sample from the same population? Do you know what I mean? If it's a sample from the same population, then you have two different samples. If it's the same people, then you only have one sample, and probably the test is not valid because you don't have two independent samples, right? The two-sample test is only valid if you have either two independent samples or you have this specific treatment control situation. And if you have, like if I took a sample of 10 people out of the, or I don't know, 50 people out of the class, and then asked you something now, like, I don't know, had you fill out evaluations on the class now, and then had you fill out evaluations immediately after the final, and to sort of see if taking the final makes you think better or worse about the class, that would not, I couldn't compare those two samples using a two-sample test because it's the same people and they're not independent. You know, probably to some extent at least, the people that like the class now are likely to like the class then, right? Okay. All right. Any other questions about that? I guess let's take a quick break. If I'm going to take a break, I should take a break now probably. It's a pretty good stopping place. I still have a little bit of chapter 26 to talk about, t-test, and I'll talk about the like, when do you use the sample SD versus the population SD kind of issue. And then I'll, do 27, 29. Okay, quick break. Okay, so okay, so I want to finish up chapter 26. This is the general structure of hypothesis tests that I've done is true for chapter 26, whether it's a Z or a T-test. Same structure also for chapter 27 when you're doing two-sample test. But yeah, one more issue I want to talk about for Z-tests, and then I want to talk a little bit about T-tests. So there's this issue I talked about before, which is basically which SD. You always want the SD of the box, okay? So always want SD of box. And the box is the population. So if you have two SDs floating around, what you want to ask yourself is basically if you know it, so if you know the SD of the box or implied by the null, use it. If not, use sample SD, which is the bootstrap method. And if you're confused, I think that the reason why this is confusing to people is that people don't think hard enough about what the population is. So I think that's my main like hint or suggestion. So if confused, so you sort of think, who is actually in the box? Okay, so the people in the box are the people that the sample is from. So the problem will say something like a simplest random sample of Berkeley students. So Berkeley students are in the box. And then you sort of think, well, do you know the SD of all the Berkeley students? Well, maybe, maybe not. Is it implied by the null hypothesis? Maybe, maybe not. So if it isn't, if you know the box is Berkeley students and you don't know the SD of that population and it's not implied by the null hypothesis, then in that case you're going to use the sample SD. Otherwise you'll use the population SD. So there's a question?
Doesn't the null hypothesis only tell us like one thing about the population? Like you told us like the average is the same. You can't assume that it's also the same as the SD.
Yeah, that's right. So he's bringing up the point that the null hypothesis typically only tells you one thing. It tells you maybe the average of the box or something else. But if it tells you the percentage of ones in the box, if you're doing a sample, if you're doing a hypothesis test based on a percent, if you know the percentage of ones in the box, that's enough information to calculate the SD of the box directly. So that's a case where it's implied by the null, right? The null maybe doesn't tell you explicitly what it is, but if the null hypothesis tells you the percentage of ones in the box, that's enough information to calculate the SD of that box directly. Okay? So typically with averages, knowing the average of the box or having it told you by the null hypothesis or assumed by the null hypothesis, typically with averages that won't help you figure out what the SD of the box is, right? If I tell you the average SAT score of a bunch of people is 530, you don't have any idea what the SD is. But if I tell you that 70% of the people have SAT scores over 600, well, that's 70%, and that allows you to figure out an SD, right? If you have just zeros and ones. So another source of confusion here is that two problems may look exactly the same, but because one of them has to do with averages and another one has to do with percents, in one case, you might, with the averages, you might use the sample SD because the null doesn't help you. But with percents, knowing the percentage of ones in the box allows you to calculate the SD of the box. Okay? So the one source of confusion is not thinking carefully about what the population is. Another source of confusion is that there's this subtle issue that the answer, which one you should, or I guess what's going on, can depend on whether or not you're talking about averages or percents. Okay? Okay, so I guess one other example that I did last week was with a die roll. So if the null says the die is fair, that's another case where the SD is implied by the null. If it's a fair die, you know exactly what the box looks like, right? So you can calculate the SD of that box without using the sample SD. Okay, questions on this issue? Okay, so then the t-test. Okay, so almost everything is the same. All this structure of the null, the alternative, conclusion, all that is the same, except for the math part. So steps 3 and 4 are a little bit different. So in step 3, when we get the test statistic, is calculated based on, I should say SE, the SE calculated on the SD plus, which is equal to square root of number of draws over number of draws minus 1 times the SD. And it's the SD of the sample that you're always using for a t-test. And I'll say why in a second. But yeah, so the SE is calculated based on the SD plus, which is that little formula. Take the SD of the sample and multiply by that factor. Square root of draws divided by number of draws minus 1. So that's one difference. The second difference is that you want to calculate degrees of freedom. Which is often abbreviated DF. It's the number of draws minus 1. And use the t-table. So when you use the t-table, you can't really get an exact p-value. You can get a range. So you can say, you know, the p-value is somewhere between this and this. Okay, so those are really the main differences. Everything else is pretty much the same. So this first difference shows up for the calculation of the test statistic, and then the second part is when you get the p-value, you need to do these little bits. Okay, questions on that? Okay, so when do you use it? The number of draws is small, so less than 25. I won't give you a problem with 25 draws exactly on the final. I'll just tell you. If you did 20, if it were 25, either way would be kind of legitimate. Really, the normal approximation does better and better the more draws you have, right? Things should look more and more like the normal curve as you get more draws. So with exactly 25 draws, I guess I might be inclined to use the t. But by the rules that I've given you, 25 draws is when the normal approximation is valid. Okay, so use when number of draws is small. Sorry, I'm not sure what order I originally wrote these down when I lectured, but when you're using the sample SD. So SD of the box is unknown. Okay, so we're doing the bootstrap method. And that's why I was saying up there that when you calculate the SD plus, you're always going to be using the SD of the sample, because if you knew the SD of the box, you wouldn't be doing a t-test, okay? So part of what makes the t-test make sense is that there's a certain amount of uncertainty having to do with the fact that you're estimating the SD, and that's part of why part of why the t-test is necessary. Okay, so then this last, I guess it's not the last bit, but this next bit is that the contents of the box roughly follow the normal curve. So in practice, this is actually fairly hard to know, because if your sample size is pretty small, like 5 draws or something like that, there's no way that if you draw a histogram for 5 draws that you're going to get something that looks like a nice smooth normal curve. It's only 5 points. So you really should have some idea about the process or the data in general. Like if I know I'm dealing with SAT scores, a lot of times SAT scores follow the normal curve, heights follow the normal curve. A lot of examples we've done follow the normal curve, right? Incomes, not so good. Okay, so you should sort of be suspicious if something has to do with incomes. The book does a lot of examples in this section having to do with measurements. So, and we didn't talk about that much, but I sort of basically said if you have measurements, it's reasonable to think that the draws are going to look fairly normal, or the box is going to look fairly normal. And it's pretty abstract. If you're thinking about like taking repeated measurements of something like the length of the eraser, you know, it's sort of soft and maybe a little bit different on each side. And if I gave it to 5 different people, they might all have a slightly different measurement. So why should those measurements follow the normal curve? Well, in practice, they often do. Okay, so for those measurement processes, that's a common context for something like this, is that you make a couple of measurements and then figure that it's going to roughly follow the normal curve. For exam purposes, I would like you to check sample average plus or minus 2 SD pluses. And that should be in the range of possible values. So it shouldn't go below 0 if I'm measuring the length of an eraser or something like that. And in general, it shouldn't, you know, be too weird. So let's see. What was I going to say? Oh yeah, so I wanted to say you'll never do a t-test for a 0-1 box, because this won't be true. If you only have 0s and 1s in your box, they won't follow the normal curve. Okay? So there's no reason to do a t-test in that situation. So I won't do that to you. I won't give you a 0-1 situation where the number of draws is small. There are other kinds of hypothesis tests that can be done in real life, but I won't do that to you. Shoot, I feel like I'm forgetting something here. I didn't write this one down. See, small draws. That's that. That's that. Is that it? Am I forgetting something here? I think that's right. I think that's all. For some reason I have it in my head that I had a 4th thing written down. I didn't bring this part of it with me. Okay, so I think that's right. Yeah? So if SD of box is known, and box follows the normal curve, you can do a z-test. Even if the number of draws is less than 25. So the only reason why for the z-test we want the number of draws to be large is because That's in general what's required for the sample, for the probability histogram to look like the normal curve, is you have a large number of draws. Well, if you start out with something that looks like the normal curve, you don't need to have a large number of draws. So you should be okay doing a z-test if you actually know the SD of the box. That's a little bit strange in practice because if you're, you know, the purpose of the hypothesis test is to figure out something about the box, right? Like the average of the box. And actually, if we're thinking about doing a t-test at all, like I said, it's not a 0-1 box. You're only talking about averages. Well, if you think about this thing here, the issue here, which SD, typically if the null hypothesis tells you something about the average of the box, there's no reason why you would know the SD of the box, right? And in fact, it would be a little bit strange to know the SD of the box, but not know the average of the box, right? So that's the only case where this would come up, is if for some reason you were told the SD of the box, but you didn't know the average of the box. And so you do a hypothesis test for the average, but SD of the box is unknown. Could happen, but it's pretty rare to think about that situation. Okay, any other questions, thoughts? Okay. So that's that. I guess I'm just going to zip through, saying just a little bit about chapter 27 and 29. So chapter 27, the first part of the chapter does a little bit of like probability stuff where we find the SE for the difference is equal to square root of SE1 squared plus SE2 squared. Okay. This is also valid for the sum of two random things. So I did these examples with like 100 coin tosses and another 100 coin tosses. If you take the sum of those two sets of 100 coin tosses, this formula works. If you take the difference between the number of heads in those two sets of coin tosses, formula also works. Okay? So that's that formula. And then this works in general for two situations in the context of hypothesis tests. So OK for two sample test when you have either two independent samples. They could be either with or without replacement. So that's one situation. And then the second situation is the specific kind of treatment control situation. Okay, so that's really the main idea of chapter 27. And I already talked about these a little bit, so maybe I'll just leave it at that. It also was pretty recent that I lectured on it. And chapter 29, there's basically two issues. Data snooping multiple tests is one issue. And the main thing that I said about this is, the main thing I would like you to know, I guess, is that if the null hypothesis is actually true, not just assumed to be true, but actually really true, fact, then if you do a hypothesis test, the only thing that's going on is randomness, right? There's no systematic difference or anything like that. So the only way you're going to reject the null hypothesis is if you randomly get a result that's really far away from the expected value. So in that setting, the chance of getting a p-value less than 5% is 5%. Okay? So that's that idea that came up in several different contexts we talked about. So then if you do multiple tests, do lots and lots of tests or something like that, then eventually you'll get a p-value less than 5% just randomly. So that's one thing. And then the other thing is this one-sided, two-sided test that I talked about in some depth. Okay, so we've I think talked about that enough probably today. Okay, any questions anyone wants to ask? Okay, so I think everything you need to know is I've told you already, but you might, keep an eye on BSpace or on your email. If I put any announcements on BSpace, I'll make sure that I send emails out about it. So if there are any last-minute details or anything. Okay, other than that, it's been fun. Thanks, and I'll see you at the final, if not sooner. Okay, bye.